So today we're going to talk about the fractional quantum Hall effect at the half-field Landau level. And we're going to describe that state as a superconductor of composite fermions. We'll see that this description gives us a way to understand a very exciting and unique phenomenon, which is a non-abelian quantum Hall state. A non-abelian fractional quantum Hall state, we'll talk about that in this video. Before doing that, let us remind ourselves what does composite fermion theory tell us about the physics of a half-field Landau level. Well, you know, composite fermion theory takes the problem of interacting electrons with a density n and a magnetic field B, and maps this problem, at least at the mean field approximation level, maps this problem onto the problem of composite fermions of the same density, but a reduced magnetic field, which is the difference between the external magnetic field and the one formed by the flux tubes carried on the composite fermions, 2 flux quanta per each composite fermion. Now, for the particular case of a half-field Landau level, this delta B is 0. So the mapping takes electrons in a magnetic field and make them composite fermions at 0 magnetic field. And then we can ask, what is the phase that usually fermions at 0 magnetic field form? And the answer is, of course, a metallic phase, a compressible phase, a Fermi liquid if you want. And we saw that this phase is very useful and very successful in explaining the physics of the nu equals 1/2 state, which was indeed a compressible state where the Hall resistivity was not quantized and where there was no energy gap. Now, we want to ask, can there be other states that these composite fermions at delta B equals 0 form? Not a compressible state, not a Fermi liquid state. Are there any other states for fermion at 0 field? Of course. For example, a superconductor. Will such a state be useful to describe a physically observed phenomenon? Well, let's see that. So let's look at what happens, just a measurement of ρxx and ρxy between filling factor 2 here and filling factor 3 here. What do we see? We see, first of all, that it's a pretty rich filling factor range. What we see at the upper half of the plot is the Hall resistivity, and at the lower half of the plot, the longitudinal resistivity. And we see lots of quantum Hall states. Some have an integer value of ρxy, or sigma xy rather, an integer value like this and this, where the value is 2, and this, where the value is 3. And others have fractional values, like here, and like here, and most importantly for us, like this one. This plateau, that is accompanied, like all other quantum Hall states here, with accompanied by a vanishing longitudinal resistivity, this plateau comes at a half-field Landau level, at a filling factor of 2.5 or 5/2. Now, that state is going to be our focus of interest today. I'm not saying that all the other states and all this non-monotonic and somewhat jiggling structure is of no interest. What I'm saying is that this interest will wait for a future video. Today, we're going to look at 5/2. So how do we look at filling factor 5/2? The first thing we do is we say, well, 5/2 are 2 plus 1/2. That can be proven. So it's 2 field Landau levels plus half a field Landau level. If the cyclotron gap between the Landau levels is a very large energy scale in the problem, which happens in the limit of a strong magnetic field, then those 2 full Landau levels are kind of inert, like core electrons in atoms that have many shells of electrons. So we're going to think about them only as something that happens well deep under the chemical potential. And we're going to focus on the half-field Landau level. So look what happens here. We have a half-field Landau level at 5/2, which behaves completely differently from the half-field Landau level at 1/2. At 1/2 there was a compressible state. At 5/2 we have a fraction quantum Hall state. We do the same composite fermion mapping and find delta B equals 0. And now we ask, can we describe the fractional quantum Hall state that is observed in terms of a superconductor of composite fermions? Well, the first requirement you impose on a description of a fractional quantum Hall state is that it should be fully gapped. And that requirement makes us face the first difficulty in this idea of describing a fractional quantum Hall state as a superconductor of composite fermions. Why? Because in a two-dimensional superconductor, generally, there are gapless modes. There is a gapless mode, which is the phase mode of the order parameter. It's a Goldstone mode. It's a density mode. It's like a plasmon, and it's gapless. So that is the gaplessness of that mode is something that stands between us and using this picture to describe a fractional quantum Hall state. Luckily, it's not a real problem. And the reason is that, as we already said, in order to find the excitation modes of an electronic system described in terms of composite fermion theory, we need to find the values of the resistivity as a function of Q and omega. The values of Q and omega for which the determinant of the resistivity is 0. But the resistivity is not just the composite fermion resistivity. It's the composite fermion's resistivity plus the whole resistivity that comes out of the attached flux quanta. Comes out of the motion of the flux quanta as current is moving. So the fact that there's a gapless excitation mode here at the composite fermion level does not yet say that it will remain gapless when we look at the physical excitation mode. And in fact, rather than being omega that is proportional to some to the wave vector, as it is for a gapless superconductor, at least with short range interaction, this addition of the two flux quanta moves this excitation mode to the cyclotron frequency energy scale, which is gapped. So the phase mode is gapped. There's a second difficulty, and it's also not a very strong difficulty, which is that for all we know, the nu equals 5/2 state is spin polarized. So we need to describe it in terms of a spin polarized superconductor of composite fermions. That's a little bit in contrast to the superconductors we are used to seeing in everyday life, niobium, aluminum, and so on, those of us who see superconductors every day. So those superconductors are generally spin singlets. Now here we need spin polarized. Fortunately, such superconductors occur. So we are now going to construct a description of this superconductor of composite fermions, and we're going to do that with a little help from our friends. And our friends in this context are Yuval Oreg and Erez Berg, my colleagues in this course, that describe in the chapters the physics of two-dimensional superconductors, and in particular the topological aspects of that physics, and that's what I'd like to remind you of. So two-dimensional superconductors that do not have time reversal symmetry, they are known as class D superconductors. In two dimensions, they carry an integer valued topological index, going all the way from -infinity to +infinity, taking only integer values. Now, what's the physical meaning of this topological index? In fact, it's very much like the kind of a cousin topological index that we know from the integer quantum Hall effect. In the integer quantum Hall effect, as you remember, if we have a sample whose I draw here only the corner of, and those are the edges, and imagine it goes far away in all directions, then along the edge we have edge modes, and the number of these edge modes is the integer value topological index. So it can be 1, 2, 3, or whatever other integer number. In the topological superconductivity case, the integer valued number nu m is the number of edge modes too. But those edge modes are now not free fermions, but rather Majorana fermions. So topological superconductors carry Majorana fermion chiral edge modes, and the number can take any integer value. Now, we are not going to go over all integers. That will take a long time. So we're going to focus on simple cases. And the simplest cases are, of course, 0 and 1. The case where there are no edge modes at all, and the case where there's a single one. In fact, there's a big difference between an even value of that topological index, like 0, and an odd number, like 1. The difference is most pronounced when you look at the core of a vortex. For an odd value of nu m, each vortex carries a 0 mode. Namely, there is an excitation mode in the core of the vortex that costs 0 energy. That 0 mode, because it costs 0 energy, will lead to a degeneracy of the ground state. And that degeneracy of the ground state is exponential in the number of vortices. Now we know about the ground state degeneracy from the context of the fractional quantum Hall effect at nu equals 1/3. Right? But then there, when we discussed that, we saw that there's a ground state degeneracy when you put the system on a torus. Here there's no torus involved. The ground state degeneracy comes from the presence of vortices. Now this is what happens. All this was a review of the physics of superconductors. We're going to use that physics to talk about a quantum Hall state. But before doing that, let's formalize it a little bit. Instead of the wire construction way that Yuval is using in his chapter, let me start from the BdG Hamiltonian and discuss the physics of two-dimensional class D superconductors, in particular p-wave superconductors, using this language. So the BdG Hamiltonian has a normal part and has a Cooper pairing part. The Cooper pairing part, you see, creates a composite fermion at the point r, capital R minus R over 2, and another composite fermion at the point capital R plus R over 2. Those 2 points cannot be the same. You cannot take little r to be 0 because you cannot create 2 fermions at the same point when they don't have a spin. So they have to be slightly separated from one another. And the function that determines this separation is short-ranged, and it's this f of little r. And in fact, it's typically so short-ranged that we can describe it in terms of derivatives. So we can describe it as dx plus idy. This choice is what's known as a p-wave superconductor. And it is so because if you Fourier transform it, you find that it has the shape of a p-wave wave function known to us from atomic physics, basically. Now, once we've done that, this Hamiltonian is a quadratic Hamiltonian, right? It has 2 fermionic operators here, 2 creation ones. The Hermitian conjugate, of course, has 2 annihilation ones. And the normal part has psi dagger psi, like all normal non-interacting Hamiltonians. So in principle, we could diagonalize this Hamiltonian by solving the BdG equations. The BdG equations are equations in terms of the energy and in terms of this spin or u of r and v of r. Once we solve this, we basically diagonalize the Hamiltonian. We can write the Hamiltonian in a diagonalized way as a sum over all energy states that we found, multiplied by the energy times gamma e dagger gamma e, the number operator for the excitations. And the excitations gamma e are functions of those u and v that we found. They can be written as u of r, psi of r, plus V star of R psi dagger of R. Now, the spectrum that we find is gapped. The spectrum that we find for that choice of f of R that we had is gapped. It's gapped in the bulk, with two exceptions. It may have zero modes at the vortex, and it has edge modes going around the sample. Let's talk a little bit about those zero modes. So first of all, as a general rule, for zero modes in superconductors, always, they must come in pairs. And the reason they must come in pairs is that the Hamiltonian, the BdG Hamiltonian that we talked about, is by definition even dimensional, right? Because we broke it into 4 blocks, and each block was the blocks were identical in their dimensions. Therefore, the total dimension must be even. Not only that, the energy spectrum has a symmetry. For any state of energy E, you have a state of energy minus E. Now you combine both of these together, and you find that if there are zero energy states, they must come in pairs. That's a crucial point, because if you have a pair of zero energy states and you separate them far away from one another, one here, the other one there, then they are protected. And the way they are protected, what I mean when saying that they are protected, is that if you perturb one of them, trying to push it up or down in energy, it will not move in energy. It may, the wave function may change, it may move a little bit, things like that, but the energy will not change, because if it does change, the other one will be left unpaired, and that cannot happen. So zero modes in vortices are stable, and they occur when the value of nu m is odd. Now, let's talk a little bit more about those vortices. And let's talk about them in the context of the fractional quantum Hall state of nu equals 5/2. Let me actually say a word about the difference between the BdG story of topological superconductivity and our case of filling factor 5/2. Perhaps the main difference is at 5/2, charge is conserved. At the BdG Hamiltonian, charge is not conserved. Pairs are created and annihilated. That's a big difference, and we'll come back to that difference at a later part of the course. But for 5/2, we are interested in a charge conserving description of superconductivity. Now, in any case, these vortices for 5/2, there are a few things we want to say about them. First of all, we know that any fractional quantum Hall state must have quasi-particles of a fractional charge. For example, for nu equals 1/3, we saw that the fractionally charged quasi-particle is just the composite fermion, because when we introduce a composite fermion at some point, we introduce a charge E, and then when we introduce the 2 flux quanta, there's a flow of charge outside because of the introduction of the flux quanta, and the amount of charge that flows outside is the number of flux quanta 2 multiplied by sigma xy. And for 1/3, that was 2/3. You put 1 in, you send out 2/3, and you are left with the 1/3 charge of the Laughlin quasi-particle. In this case, sigma xy for the half-width Landau level is 1/2, which means 2 times 1/2 is 1. So you put in a charge 1 and you send it all out. So the composite fermion, it gives you a quasi-particle, but it's a quasi-particle of 0 charge. In fact, the charged quasi-particle is the vortex. When you introduce a vortex, you don't put any charge inside. It's not it's not like a composite fermion, a composite of charge and flux quanta. A vortex is just a flux quantum, and it's a flux quantum of half a flux, just a flux, and it's a flux of half a flux quantum. So the flux, instead of being 2, is just 1/2. Sigma xy is 1/2 too. So the product is 1/4. And the charge, therefore, of the vortex, the charge that the vortex carries is a quarter of an electron charge. Now, if this is a general argument for any topological superconductor. If nu m is odd, then the quasi-particle comes not only with a quarter of a charge, but also with the degeneracy of the ground state because of the zero modes. That degeneracy, again, is on a planar geometry, has nothing to do with being on a torus, and has very profound consequences for the nature of the state, which is what I'd like to discuss now. So imagine that we have a two-dimensional system at nu equals 5/2, and we put in some quasi-particles. I should say putting in quasi-particles is pretty easy. The only thing you need is you need to go slightly away from filling factor 5/2 exactly. Either up or down, doesn't matter. Because what happened then is delta B is not quite zero. You have a superconductor with a little bit of delta B inside. And superconductor, the way it deals with the magnetic field is by accepting vortices. And those vortices are our quarter-charged quasi-particles. So generating these quasi-particles is just a matter of changing the density of the magnetic field a little bit. Now, suppose that you put those quasi-particles in. We already know their charge is 1/4. What about their statistics? So for the case of nu equals 1/3, the Laughlin quasi-particles, we saw that if we interchange the position of two quasi-particles, and if we do it slowly, the system stays in the ground state. If we start from the ground state, it will stay in the ground state, but that ground state will be multiplied by a phase factor, and the phase factor we found was reflecting the filling factor that we look at. Now here the story gets much more interesting. Because yes, when we interchange two quasi-particles, just as we did it before, if we start in the ground state and we do it adiabatically, we will stay in the ground state. But there's not a single ground state, there are many of them. So we will start in a ground state and we will end in a ground state, but it's not necessarily the same ground state. Which means that if we start from some ground state, some initial ground state, as we carry out this interchange, we do not multiply that ground state by a phase factor. We multiply it by a unitary matrix. And if we do another interchange, so let's say if this was quasi-particle 1 and this is quasi-particle 2, and we interchanged 1 and 2, if we then interchange 2 and 3, and then whatever else interchanges we wish to take, we will keep on multiplying the states by unitary matrices. And the final product will be, it's a product of unitary matrices, it will be a unitary matrix, but it will not be a phase factor. Unlike the case of the nu equals 1/3, it will not be a phase factor. It will be a product of matrices, and a product of matrices, of course, is not commutative. It's non-abelian. So the statistics of these quasi-particles is non-abelian. The final state you get depends on the order at which you do the interchanges. Now, those unitary matrices depend only on the topology of the trajectory that you take. Meaning, if you did this interchange, instead of taking this trajectory by taking this trajectory, the unitary transformation that you apply, or at least the non-abelian part of that unitary transformation, will not change. But if you deform the trajectory to this, that's a new world, that's a new unitary transformation. This is the physics, or this is the idea of a non-abelian fractional quantum Hall state. We'll see non-abelian states in other contexts as well later on in the course. A very thought-provoking concept. Now, all this was motivated by the idea of describing the nu equals 5/2 state as a superconductor of composite fermions. Now we know that there are many possibilities for that because we know there is this integer valued index nu m, which tells us how many Majorana edge modes, chiral Majorana edge modes, encircle our sample. 1 here, 0, -1, -2, -3. Each one of those is a separate candidate state for a fractional quantum Hall state at nu equals 5/2. And there are, of course, many other numbers going from -infinity to +infinity. Each such number gives us a candidate state, but we are not going to, we cannot deal with so many. We need to find out which of the candidates, if any, have a chance of being the state that describes the experimental system. The main tool for that is a numerical work. Experimental techniques recently joined the effort because now there are experimental measurements that give indications. Numerically, in fact, this state of nu m equals 1 and this state of nu m equals -3 seem to be the leading candidates, while experimentally there are many indications for nu m equals -1. So the picture is not clear yet. But to complete the theoretical picture, let me say that there are also, on top of those Majorana modes, there are, of course, charge modes. Two charge modes of the inert integer Landau levels, field Landau levels, and one charge mode of the half-field Landau level. They must exist because there are always charge edge modes to carry out the whole conductivity. So all those will be valid nu equals 5/2 states, and they'll differ by the number of edge Majorana modes. Being leaders in this competition, and for historical reasons also, those states got names, and I'll tell you the names. There's a very systematic naming scheme. This is called the Pfaffian state or the Murid state. This is called the k equals 8 state. This is called the pH Pfaffian state, standing for particle hole Pfaffian. This is called the 113 state, and this is called the anti-Pfaffian state. There are names also for a few states going right and left. They don't make much more sense than this scheme. There are, of course, reasons for the use of the word Pfaffian. I will not get into that, but I'll give you references in the notes. So this is as far as we're going to get talking about the 5/2 state. Just to summarize what we talked about, the 5/2 state we described as a superconductor of composite fermions. And we showed that at least it is possible that the superconductor that these composite fermions form will lead to a non-abelian quantum Hall state, which means that there will be a ground state degeneracy that's associated with the presence of quasi-particles and is way larger than the one you expect when you put the system on a torus. And there's a non-abelian statistics associated with these interchanges of quasi-particles. We also saw that there's a charge of 1/4 of an electron charge for the elementary quasi-particles that come with the vortices of the composite fermion superconductor. Finally, I'll also say, we looked at the experimental plot of the filling factor range between 2 and 3. We saw it's very, very rich. We saw there's much more to talk about in that filling factor range, much more than just the nu equals 5/2. But we defer this for a future video.